Okay, this is a walkthrough for CCEA Maths. It's a pure section and it's A2 from Tuesday the 28th of May. So let's take a wee look then at question 1. A curve is given by the equation x cubed plus 3y squared equals 11. By using implicit differentiation, find dy by dx in terms of x and y. So we need to differentiate this here. Differentiating this is going to give us 3x squared. Differentiating this with respect to x is going to give us 6y. And remember a wee trick. Multiply then by dy by dx. Differentiating the 11 of course gives us 0. So it says find dy by dx, so we just need to get the dy by dx bit on its own. So I'm going to take 3x squared from both sides. Dividing then by 6y. And obviously then our 3 and our 6 are going to cancel slightly, so we end up with minus x squared all over 2y. Question 2. A curve is defined parametrically by x equals at squared and y equals 3at, where a is a constant and t is a parameter. Find the Cartesian equation of the curve. So we need to effectively try and eliminate the t and get rid of it somehow. A couple of different ways of doing it. We could get the t squared on its own and square both sides here. I think it's probably more straightforward if we rearrange this. So if to try and get the t on its own here, we're going to divide by 3a. So t equals y over 3a. And now we substitute that in here. So I'm going to substitute into x equals a t squared. So x equals a upon y over 3a whole squared. That gives us x equals a upon y squared over 9. Remember to square the 3 as well, obviously. A squared. And hopefully you can see then that this a is going to cancel out with 1 of the a's here. And if I then multiply through by the 9a, I get 9ax equals y squared, which is fine. I just want to see the y squared bit first, so y squared equals 9ax. Question 3 then. A mirror ABCDE is designed in the form of a sector of a circle, which is this bit, centered at B, together with two congruent right-angled triangles, BAE and BCD is shown below. That's 80, that's 60. Find the angle EBD in radians. So we're trying to find this angle here. Because it's in radians, this here would obviously be 180 degrees or pi, as in all the way across that. And these are congruent, so they're the same size. So if we find this angle here, times it by 2, take it away from pi, in other words 180, then we'll be able to get our angle in EBD that we're looking for. So let's take our wee triangle out of this. I hope you can see that because that's 80, then this is going to be 40. This would be 60, and let's call this theta just for the minute. That's O, that's A, so we're going to be using tan. Tan theta then is going to be 60 over 40. Theta, then in radians, make sure your calculator's in radians, gives you 0.98279. So therefore our angle EBD is going to be pi take away 2 upon 0.98279, and that gives us then 1.18 radians, giving our answer then to 3 significant figures. Part 2 then says find the area of the mirror. So let's look back and look what we need to do. We found this angle here in radians, and this is a sector, so we need to find the area of this sector and then add on the area of the two triangles, so that should be okay. If this is a sector, so this is part of a circle, we need to find the radius then of this circle, so we're going to have to use Pythagoras here for 40 and 60 then to work out our radius. Alright, so to find then a radius BD then is going to be our first move. So BD squared is going to equal 60 squared plus 40 squared, and then if we find our square root, so we get 20 root 13. You can see that okay on the calculator. Yeah. So that then as a radius, that's all we need to know then to find the area of the sector. So that's 20 root 13. That is 1.18 radians. So we're going to use our formula then. Area of sector is a half r squared theta, so that's equal to a half upon 20 root 13 squared. Good to keep it in that form there because that's the exact form, multiplied by 1 point, and I've written 1.18 in the previous one, but if I can take the original value, which is 1.1760, then it's going to make things a wee bit more accurate. Put that in your calculator, you'll get 3057.6. So that's the area of this wee bit here. We now need to find the area of then of the two triangles. So it's going to be 2 times a half BH. Obviously 2 times a half cancels itself out. The 60 times the 40 gives us then 2400. So total area adding these two then together is 5457.6 centimeters squared. The three significant figures then 5460 centimeters squared to 3 significant figures. Question 4. Prove that cosec 2 theta minus cot 2 theta is equal to tan 2 theta. Sometimes tough to know where to go with these things, so I'm going to start then with the left hand side. And I notice here we have, those are double angles there, so we need to get rid of those and need to end up then somewhere with tan theta. So let's change this to a 1 over sine 2 theta and change this then. Cot, remember, is the inverse of tan, so we can write it like that. So let's go for 1 over sine 2 theta minus cos 2 theta all over sine 2 theta. Hopefully we're okay with that move. Good thing about that is we now have a common denominator. So 1 minus cos 2 theta all over sine 2 theta. One thing I am noticing, and again, sometimes it's guesswork here, you sort of head down with these things and then you don't get any further, but because this is a double angle, this one here is a single angle, so I want to try and get rid of our double angle. So if I use my double angle formula for each of those, we may be able to get somewhere. So 1 cos 2 theta, I know is 1 minus 2 sine squared theta. I like that one for a couple of reasons. You know, there's 3 different versions of the cos double angle, but 1 take away 1, so that means that disappears, which is good news. And then the sine 2 theta, again using your formula for that, 2 sine theta cos theta. So let's tidy that up. 1 minus 1, so that's good, and a minus minus, so it's a plus. So we get 2 sine squared theta all over 2 sine theta cos theta. I think we're almost there. So the 2 cancels, sine theta cancels with that, so we're left with sine over cos. And even I know that that is the same as tan theta. And on then to part 2. Hence, find the exact value of tan pi over 8. So, using our previous thing, because we have to use the previous thing because it's used the word hence. So, we know tan theta equals cosec 2 theta minus cot 2 theta. That means tan pi over 8 equals cosec pi over 8 then times 2 pi over 4 minus cot pi over 4. That's going to be the same as 1 over sine pi over 4. If you want, I suppose, 1 minus tan pi over 4. Those would be the ones that we know. Again, put that in your calculator, though you should know it. Sine of pi over 4 is the same as sine of 45, which is 1 over root 2. So this is 1 over root 2. Tan of pi over 4 then is 1. 1 over root 2 just gives us then root 2, take away 1. Question 5 then, a function f is defined by f(x) is x squared take away 8 for all real numbers, and x has to be greater than or equal to 0. State the range of the function, so we want to know what numbers we can get out of this, if these are the ones then that we can put in. So just a wee bit of sensible thinking should really give you your answer. If you put in any number bigger than or equal to 0, if you put in 0, you're going to get minus 8. If you put in something bigger than that, the number just gets bigger and bigger and headed off to infinity. So it's going to be, our range is going to be f of x greater than or equal to any number bigger than minus 8. The other way, if you wished, is you could do a wee graph. So x squared minus 8, I hope that we know that's just a quadratic curve crossing then at minus 8. So the numbers you're putting in are x greater than or equal to 0. So what numbers in can you get out? It's going to make anything then bigger than minus 8. Find the inverse function f to minus 1 of x, clearly stating its domain. So we know our function is y equal x squared minus 8. That means we could rearrange it as x squared equals y plus 8. So x equals the square root of y plus 8. That means our inverse function, right in the same format that they have up there, is x, the square root of x plus 8, where x is a member of the real numbers and x is greater than or equal to minus 8. Next part of function g is defined by g is x modulus of x minus 3, where x is a member of the real numbers. On the axis below, sketch a graph of y equals g of x. So if you think about this, it's a bit like y equals x minus 3. So that has a gradient of 1, and it crosses the y-axis then at minus 3. So gradient of 1 is going to head this way here. And so I'm doing a wee dotted line here. And then it heads like that. And of course the modulus function then reflects anything below the x-axis above it. So we would have this function here. For a sketch, I would always want to see where it crosses or touches either axis. So if that's a reflection there, then that's 3. Of course, that should be minus 3. And then this crosses here at 3 as well. Find the composite function g of f of x. So that means any time I see an x in the g function, I'm going to exchange it then for an x squared minus 8, which was my f function. So the function gf modulus, so I'm changing my x now for an x squared minus 8 minus 3. So tidying that up then. X squared minus 11. Again then where x is a member of the real numbers and x is greater than or equal to 0, because that was the f function is then what's going to decide then the domain. (5b) then, the graph of the function y equals h of x is sketched in figure 2 below. On the axis below, sketch the graph y equals a third h of 3x, and clearly label the images of the points P and Q, so they need to go on. So the 3x squeezes everything 3 times closer to the y-axis. That's what the 3 does there. And the third squeezes everything down here. It doesn't matter which order in this particular one, which case you do things. So this Q is going to go down 3 times closer, so it's going to go down into a 2, and this is going to squeeze in 3 times closer. That then is going to go to there, and of course the 3 then is going to go down to 1. Now of course we can just draw the thing the same size and just do a different scale. That's totally fine. So my shape looks a little bit like that, and then where possible use a ruler. It runs like that. So there's my Q, and there's my P. So Q has been squeezed down 3 times, so it's changed from a 6 into a 2, and the point P then is at the point 1, and that also then is now at the point 1 as well. Part 2 then, on the axis below, sketch the graph of y equals 6 minus 8 of x. Clearly label the points. Now this is a different kettle of fish here, so this is a different. First of all, I'm going to rearrange it because I don't like the way it looks. So y equals minus 8 of x plus 6. This minus here reflects it in the x-axis. This 6 moves everything up 6, and this is one of the ones where it's important. So this is like y equals a f of x plus b type 1, and this is one of the 2 where the order is important. So the a bit needs to be done first, so we need to reflect it first and then move it up 6. So let's take a look then and see if we can get this to work. Just give me a second. So here's the original. This is all going to get reflected here. So let's draw just a wee sketch here, and we'll be able to see. And it goes into there. That will be then at the point minus 6, and that'll be minus 3. And then we need to move everything up 6. So the minus h of x reflects it here, and then the plus 6 moves everything up. So there's your minus 6, there's your minus 3. Everything moved up 6, then that's going to be on the origin, and then that's going to be the 0.33. So that's what we need to draw on here. So that there will be at the 0.3. This is the 0.3, and then that's the 0. You might want to have a wee bit of working out, what was he kind of showing here, for your minus 6, your minus 3 on that point, but there's in your final shape. Okay. Question 6, the expression 8 sine x plus 15 cos x can be written in the form r sine x plus a, where r is an integer and alpha, sorry, it's not a, it's an alpha. Alpha is between 0 and 90. So r sine x plus alpha. If I do my expansion out of this, it's r sine x cos alpha plus cos x sine alpha. And so it's from this that I can see there's the sine x and there's that, and so the 8 over whatever it's going to be is going to be the cos alpha, and so on. 8 and 15 are two parts of a Pythagorean triple, so we can work that out. We know r squared is going to be 8 squared plus 15 squared, and it gives you an r value then of 17. So if I start then with my 8 sine x plus 15 cos x, and I can write that then as 17 upon 8 over 17 sine x plus 15 over 17 cos x. Then I can set it up whichever way I want. So that then is going to be, if you want, the cos alpha. So cos alpha then is 8 over 17. Shift cos 8 17. And that gives me then 61.9 degrees. Of course, you can kind of set it up. You can do it by tan as well, or you can do it by sine or whatever. So that's going to be 17 upon sine x plus 61.9 degrees is my other way of writing that. They've asked for two things really. They've asked for the r and the alpha. So just write them finally, although they are there anyway. R is 17 and alpha then is 61.9 degrees. Hence or otherwise determine the maximum value of 18 over 8 sine x plus 15 cos x plus 23 and find a corresponding value of x. So we could rewrite this. Obviously this here is the wee bit that we worked out in the previous question, so that's going to be 18 over, how did we rewrite that? 17 sine x plus alpha plus 23. So you need to think about this slightly. If we want to make this quotient here, this fraction thing, a maximum, we want to make this as big as possible and this as small as possible. So you want that this bit here needs to be then as small as possible. So the maximum occurs whenever the denominator is a minimum, if that makes sense. So minimum value of sine x plus alpha, the smallest value you can get out for any time you hit sine is of course minus 1. That means then the maximum value is going to be 18 over If that's minus 1, that then is going to be minus 17, which is 18 over 6, which is going to be 3. So when does this happen? This happens when sine x plus alpha equals minus 1. When is sine minus 1? That then is when the angle is 270. So x is 270. X plus, I kind of lost my angle again, 61.9 is 270, and that gives us then a value to 3 significant figures of 208 degrees. Question 7 then, use a trapezium rule with 3 ordinates to find an approximate value for this. So 3 ordinates means 2 strips, so we need to split this in 2, so it's simply going to be 2, 2.5 and 3, and so our h in this case is nice and straightforward. It's going to be 0.5, hopefully that makes sense. So if we do out our table here, we have x here, and then we're going to have x squared over x plus 3 upon x minus 1. And the numbers we're going to be putting in for x then are of course going to be 2, 2.5 and then 3. So to get our y0 point, we're substituting in then the number 2. So on the top you're going to have a 4, and then you have a 5. Then you have a 5 times a 1, so it's 4 over 5, or if you want then 0.8. If we sub in 2.5, it gets a wee bit messy, but you can take my word for it. If you substitute the number 2.5 in here, 2.5 squared is 6.25, we have 5.5 here, and then 1.5 here, and you multiply it. It gives us our y1 value, which is 25 over 33 is our exact value, or 0.75. Repeating. If you sub in the number 3, we have 9 on the top, and then 6 times 2 on the bottom, so that's going to be 9 over 12, which is 3/4, or 0.75, and so we have that. So using our trapezium rule then, our area is h over 2 y0 plus 2 upon y1 plus y2. Normally, you have more ordinates than this to kind of deal with, but that's what we're going to have. So this is 0.5 over 2, y0 0.8 plus 2 upon 25 over 33 is our more accurate option for it, plus 0.75. And again, take a wee bit of time, put that into your calculator, and we get 0.766. Part 2 then says use partial fractions to calculate the value of this. So a fair bit to do here. First of all, for our partial fractions, the first thing we always check with partial fractions is the power of the denominator equal to or higher than the power of the numerator? Sorry, that should be the other way around. But this is a quadratic in the top and a quadratic in the bottom, so we need to do a long division first of all. So we're going to do x squared, multiplying this out, x plus 3, so x squared plus 3x minus x, so that's plus 2x minus 3, and divide that into our x squared. That goes in one time. This times this gives me x squared plus 2x. minus 3. So we get then a remainder of minus 2x plus 3. So what does that tell us? We just need to be a bit careful with this. This was a top-heavy fraction, and we've now changed it. So this tells us that x squared over x plus 3 upon x minus 1 can be rewritten as 1 plus minus 2x plus 3 x plus 3 upon x minus 1. Hopefully we're okay with that. You need to be careful changing from here to here. So we're going to take this bit and do partial fractions then for that. So minus 2x plus 3 all over x plus 3 x minus 1. It's just two linear terms, so we're going to write that as a over x plus 3 plus b over x minus 1. That gives us minus 2x plus 3 equals a upon x minus 1 plus b upon x plus 3. I'm going to let x equal 1. If I let x equal 1, I get 1 equals 4b. That gives me b is a quarter. I'm going to let x equal minus 3. That gives me then 6 plus 3 here, so that's 9 equals minus 4a. Obviously this bit disappears, so that means a is minus 9 over 4. So where are we? Let me just check if another page is working here. Yeah, plenty of space, so we're okay. That means our original question can now become, don't forget the 1, obviously, the integral in between 3 over 2, our a is minus 9 over 4, so I'm going to bring the 9 out the front, and then, sorry, the minus out the front, and then 4 upon x plus 3. I've forgotten the 1, ridiculous, sorry, 1 is here, plus 1 over 4 upon x minus 1 dx. Hopefully you can see that these are just going to be ln functions, and funny enough I normally encourage people to change this to a 9 and 4 here down here, but it would have been easier if you leave the 9 over 4 on the top, because you can kind of see then where it's going to come out. But if we integrate now, we should be in a shape to be able to work this out. So let's move this back up if we can still see the bottom line if I set it up in a decent enough way. Great, but it'll do. So let's integrate. Again, be careful. Hopefully I'm not moving too quickly for people. Integrate the 1. I get an x. Take away. So again, if you wanted to take the 9 over 4 at the top and just kind of take it out the front, but it's going to be 9 over 4 ln x plus 3 plus a quarter ln x minus 1 between 3 and 2. So let's see where this takes us. Again, just nice and slowly. So summing in the number 3 minus 9 over 4 ln 6 plus a quarter ln 2. Take away, substituting in the number 2, take away 9 over 4 ln 5 plus a quarter ln 1. That gives me then 3, take away 9 over 4 ln 6. 6, in fact, you know what, I should take away the 2 there, but that's okay. Plus a quarter ln 2 minus 2 plus 9 over 4 ln 5. The easiest thing really there is to change the 3 and the 2 then just to a 1, but you still then have those 3 terms, and it's a case now. Sorry, the quarter ln 1 of course disappears. Ln of 1 is just 0, so that's okay. And final answer then, so just plug all that into your calculator and you should end up within the 0.763, the 3 significant figures. Part 3. Explain how the use of the trapezium rule in part 1 could be modified to obtain a better approximation to the integral, because obviously we're 0.766, which for the, I think was not right for the trapezium rule, and it's 0.763 is the more accurate one. And of course, because we want to use 2 strips, so the answer would be to use more strips to improve approximation. Okay, so the population P in a housing development grows at a rate proportional to the population at any time t years. This can be modelled by the differential equation dp by dt equals kp, where k is a constant. The initial population is p0, so that p equals p0e to the kt. So reasonably straightforward. We're starting off then with dp by dt equals kp. Separating out our variables here then, so dividing then by p, we will have 1 over p integral dp multiplying through then by dt equals the integral of k dt. Hopefully you're okay with that move. So integrating then both sides, 1 over p goes to ln p, and this with respect to t then is going to go to kt plus c. Now we're told that the initial population is p0. Initial of course means then when t equals 0, the population equals p0. So if I substitute that information in, that means then that's going to disappear, and it means c equals ln p0. So changing my c then for an ln p0, so I have then ln p equals kt plus ln p0. ln p minus ln p0 equals kt. Using our laws of logs, we have ln p over p0 equals kt. Getting rid of another log, we get then p over p0 equals e to the kt, and we're a line away then. P equals p0 multiplied through then by p0 is e to the kt. Okay, given that the initial population doubles in 5 years, find the exact value of k. So our equation is p equals p0 e to the kt. If the initial population was p0, then if it doubles it's going to be 2 P0, and we're going to use that then to try and work this out. So that means we know that 2P0 equals P0 e to the kt. That means sorry, 5 years, that means our 5 is t as well. Sorry, apologies. I can change my t then for a 5 here. Let's change it actually up here. .5k, I can divide then by P0, so I get e to the 5k equals 2. That means 5k is ln2, and that means k then is a fifth ln2. Find the number of years until the initial population is trebled. So if the initial population is trebled, then p is obviously going to give me 3p0. The equation we were using was p equals p0 e to the kt. Now we can go 3p0 equals p0 e. Of course, we've worked out our k now. It's a fifth ln 2 t. The p0s are going to cancel. So we have e to a fifth ln 2 t equals 3. If we take logs in of both sides, the e is going to disappear, so we have a fifth ln 2 t equals ln 3 t equals ln 3 divided by a fifth ln 2, and that's just going to be a calculator option then from here. That gives us t is 7.92 years. It asks for the nearest year, therefore time is 8 years. State a limitation of this model. Well, if you read back to the very start of the question, it does say that it's in a housing development. So, I mean, this here is kind of growing and it's going to grow to infinity, and that obviously can't happen in a housing development. So, something like that would be fine. So, if we then say population cannot grow indefinitely, in a housing development. Something like that then would be fine. Okay, question 9. A curve has equation y equals x minus 5 upon ln x. Show that dy by dx equals 1 minus 5 over x plus ln x. So hopefully we can see that this is a product rule question. So we were going to let u equals x minus 5, and we're going to let v equals ln x. du by dx is 1. dv by dx is of course 1 over x. dy by dx is u dv by dx plus v du by dx. U dv by dx, so this times this is going to be x minus 5 upon 1 over x plus v du by dx, then plus ln x. You can write this a couple of different ways, really. X minus 5 over x plus ln x. That was a silly way to do it, really, but separating it out, you're going to get then 1 minus 5 over x plus ln x, which is what's required. Part 2 then, show that the curve has a turning point between x equals 2 and x equals 3. So, if it has a turning point between 2 and 3, then if here's 2 and here's 3, then the gradient here is going to be negative, the gradient's going to be positive, or the other way around. So I'm expecting a positive number and a negative number whenever I put 2 and 3 into the gradient function, and we've just worked out the gradient function in the first one. So we have dy by dx equals 1 minus 5 over x plus ln x. So at 2, we're going to have 1 minus 5 over 2 plus ln 2. If you put that into your calculator, you get minus 0.80685. At 3, 1 minus 5 over 3 plus ln 3, with 0.43194, and it's the fact that this is a negative and this is a positive. Alright, so since we've had a change of sign, between 2 and 3, there must be a turning point in this region. You also might want to mention the fact that it's continuous as well. It's a continuous function, so there's no gaps in between 2 and 3, otherwise that might mess it up. Okay, by taking 2.4 as the first approximation to the x-coordinate of the turning point, use the Newton-Raphson method once to find a better approximation. So we need to differentiate this again. So we're going to let our f of x equal the dy by the x bit, so 1 minus 5 over x plus ln x. That means then f dash of x, differentiate this, it disappears. This is, remember, minus 5x to minus 1, so take away 1 from the power is going to give me minus 2, and multiply then by the old power, which is our minus 1, so the minus disappears. Either way you get 5 over x squared. Take your time with that if you're not sure. Differentiating ln x, 1 over x. Now in the first part with a product, but with no products here, with 1, 2, 3, just all separate terms, so that's all fine. Okay, so xr plus 1 equals xr, take away f of xr, f dash xr, which is our Newton-Raphson method. So xr plus 1 5 over x plus ln x, and that's the wee xr, and then our differentiated one is 5 over xr squared plus 1 over xr. So here's our formula. We're starting with 2.4, so I'm going to substitute in a 2.4 then any time I see this. So it's going to be 2.4 subtract 1 minus 5 over 2.4 plus ln 2.4, 5 over 2.4 squared plus 1 over 2.4 So by the time you're typing all that into your calculator, you're doing well, but it gives then 2.56 then to 3 significant figures. Question 10a then is an integration, and hopefully you can see then that we have x to the minus a half multiplied by ln x. So we're going to be using then integration by parts to do this. This is one of these odd ones, of course, where it's ln x, which we picked then to be u. It just makes things work out. So we're going to let u equal ln x, and then dv by dx is x to the minus a half. Du by dx then is 1 over x, and v, add 1 to the power, and then divide by the new power. So dividing by a half is the same as multiplying by 2, so it's 2x then to the power of a half. So our formula, which I maybe should have written out first, integral of u dv by dx equals uv minus the integral of v du by dx. So my uv is 2x to the half ln x minus the integral of v times du by dx. So it's 1 over x times 2x to the power of a half. So that's 2x to the power of a half ln x minus the integral. So if I take away 1, because that's 1 over x, so that's x to minus 1 multiplied by this, so I subtract 1 from this part, so it's 2x to the minus a half dx. That gives me then 2x to the half ln x minus, so add 1 to the power, divide by the new power, which is a half. 2 divided by a half, that is 4. So it's minus 4 x to the power of a half plus c. Okay, so we're going to be using substitution here. So just a wee thing then about substitution. So the integral of f of x dx is equal to the integral of f of x dx by du. We're using the substitution u squared equals x squared plus 4. This is a tough one. Normally you can rearrange to get the x on its own or the u on its own. So it's much easier actually just to do this implicitly, if this makes sense. So we're going to go 2u du equals 2x dx. That means dx by du equals, what am I doing here? I'm doing that divided by that, so it's then going to be u over x, isn't it? So that then is hopefully fine. Still a wee bit of messy things to do here, but we'll kind of sort it out. So let's see if we can start to work our way through this. So it's root 5 and 0 of x cubed all over. That, of course, then is going to be u times dx by du. That is multiplied then by u over x du. So a bit of a palaver there to try and work out, but that's okay. So first of all, we need the x. So that means x squared is equal to, what am I doing here? U squared minus 4. It's going to be easier for integrating if we just go x is u squared minus 4 all to the power of a half. The other thing we're going to want to do then is change our limits. So where can I do that? Change limits. U squared equals x squared plus 4. So if x is root 5, u is going to be, so root 5 squared gives me 5 plus 4. Square root of that then is going to be 3. And 0 squared plus 4 square root of that is going to be 2. So if x is 0, then u is going to be 2. So my new limits then are 3 and 2. And we have u here. We have u on the top. We have on the bottom u squared minus 4 du, and on the top here, can you see this? So if this is x cubed and this is x, if we cube this, we change this into a 3. So it's going to be u squared minus 4 to 3 over 2. Goodness. So the plan was to get rid of all the x's, so we've managed to accomplish that, but it's still fairly messy looking. So this u is going to cancel with this. And then my 3 over 2 and my half here. So we're going to, this is the same thing, so we're going to subtract the two powers. So 3 over 2 take away 1 over 2 gives 2 over 2. So actually what we're end up with is really quite handy. We just end up with then u squared minus 4 du. So if you're still with us, you're in good shape. We're now ready to integrate finally. Add 1 to the power divided by the new power, so that's going to give me u cubed over 3, take away 4u, and that's in between 3 and 2. Substitute in the number 3. U cubed is 27 divided by 3, so 9, take away 12. Substitute in the number 2, 2 cubed is 8 over 3. Take away 8, and calculate that. We end up finally then with 2 1/3. So a fairly tough one there that we're going to look through. Remember, we changed our limits to get from there to there. We're finding our dx by du. This is quite an unusual thing here. Again, we don't do this too often in terms of working this bit out and then working our way through there. Hopefully that made sense okay. Question 11. The graphs of the curves y equals sine 2x and y equals cos 2x are shown in figure 3 below. The curves intersect at the points A and B. Show what the coordinates of A and B are that. So if we're trying to work out where two lines intersect each other, we put the two equations equal to each other. So we would write obviously then sine 2x equals cos 2x. If I divide both sides by cos 2x, I'm going to get tan 2x equals 1. We're very clearly here in radians, so hopefully you can see. That's pi over 4, so it's less than pi over 4, and then 3 pi over 4, so you can kind of see the sort of solutions in that we're looking for. But I mean, we could do it a couple of different ways, really. But the two bits, so tan 2x is going to equal 1. So if we do our basic angle, it means 2x is going to be pi over 4. Our next possible option is 5 pi over 4. Hopefully I'm not going too quickly for you there. If you wanted, you could use your cast diagram. C-A-S-T. Your basic angle ends up being here, 45 degrees or pi over 4. And your next one is here. And so those then are the two angles then that I have written down. That's for 2x. Obviously then for x, it's going to be pi over 8 and 5 pi over 8. So the top section of a trophy is a flat metal sheet modelled in the shape of the shaded region R. Calculate the area of this region. So we need to find the area of this region here. So what we do is we're going to integrate between these 2 points here, and we get the one on the top, take away the one on the bottom. So be careful here, we know which one's which. This one here is clearly the sine one, so it's on the top of this region. So we're going to do sine 2x, take away cos 2x, and integrate those in between those 2 points. So let's see what that gives us. So it's going to be area equals the integral. The 2 points we found in part 1 were 5 pi over 8 and pi over 8. And it's going to be then sine 2x take away cos 2x dx. Integrating sine 2x is going to give us minus a half cos 2x. Integrating minus cos is minus a half sine 2x. 5 pi over 8 and pi over 8. Substituting this in then, so the 5 pi over 8 is going to be minus a half cos 5 pi over 4 minus a half sine 5 pi over 4 minus a half cos pi over 4 minus a half sine pi over 4. So what are these going to give us? Cos and sine, you're in the third quadrant here, so those are both going to be negative, and it's the equivalent then. So cos 5 pi over 4, I mean, just put in your calculator, you get 1 over root 2 each time, but it's a negative 1 over root 2 for the 5 pi over 4, so this is going to give us 1 over 2 root 2 plus 1 over 2 root 2 minus 1 over 2 root 2 minus 1 over 2 root 2. Now, this plus this, 2 over 2 root 2 minus 2 over 2 root 2. Get in there. Give me a second. I mean, there may be quicker ways to cancel this down, but that's plus plus, so you get 4 over 2 root 2. That's the same as 2 over root 2. Rationalising the denominator, then you just end up then with root 2. A circle has equation x squared plus y squared equals 4. The base of the trophy can be modelled as a solid formed when the area bounded by this circle, the y-axis and the line x equals 1 is rotated through 2 pi radians about the x-axis. Find the exact volume of the trophy base. So this here, the radius is 2 obviously, and its centre 0, 0. So the circle looks very slightly like that, where that's 0, that's 2, and that would be 2. It's the y-axis and the line x equals 1, so there's your base shape there, if that makes sense, and once again that's rotated around, so we need to try and work it out like that. So our volume for working out these things is obviously going to be V equals pi integral between 1 and 0 of y squared dx. So that equals pi between 1 and 0. Y squared is then 4 minus x squared. Integrating then 4x and 1 to the power x cubed divided by the new part over 3 and between 1 and 0. Substitute 1 in, so it's 4 take away a third, and then the 0 then gives us nothing. So 4 take away a third gives us 3 2/3, which then is 11 pi over 3. Okay, question 12. Prove that the sum of n terms of an arithmetic progression with first term a and last term l is this. So let's write out what our sum is actually going to be. First term, next term is a plus d, next term is going to be a plus 2d, and so on. And this l is like an a plus n minus 1d, but because we've written it in terms of l, that's okay. Plus dot 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 plus. The last term is of course l. The penultimate term then is l take away d. Hopefully that makes sense. If we then write this same thing out again, only backwards, l plus l minus d plus l minus 2d plus dot 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 plus a plus d plus l. A nice wee trick happens then whenever you add these two things together. So 2s of n, this gives me a plus l. A plus d plus l take away d, the d's cancel, and we just end up with an a plus l. A plus 2d plus l minus 2d, the 2d's cancel, a plus l. A plus l, sorry, that final one should be an a, of course. A plus l. So how many of these do I have? There are n of them, of course. So it's 2 s of n equals n a plus l. So that means s of n equals half of n upon a plus l. The first term of an arithmetic progression is 7. The last term is 79. The sum of the progression is 1075. Find the number of terms. So we've just used this formula. So we've just proven this formula. So let's actually use it. Half of n upon a plus l. So that means 1075 equals a half of n upon 7 plus 79. You can do this a load of different ways, I suppose. So 1075 equals 7 plus 79 is 86. So I would say then 43 n. This divided by this, then it's going to give us 25. Find the common difference. Just give me a second to get the formula. Use the nth term formula here. So the nth term is of course a plus n minus 1d. And if the last term was 79 and we know there are 25 terms, we can set it up then like that. So we can have 79 equals our first term, which is 7. 25 taken 1 is 24d. That means 24D is 72, so our common difference then is 3. Okay, part B, a salesman receives a bonus at the end of each year and decides to invest this money in a savings account. At the end of year 1, he invests £400. At the end of year 2, he invests a further £400 and receives 2% interest on the first year's £400. At the end of year 3, he invests a further £400 and 2% interest is added to the total sum of money which he has accumulated during the first 2 years. So the £400 that he invested in year 1 has been added to twice, so that's multiplied by 1.02 squared. The one he invested at the end of year 2, 400 multiplied by 1.02 plus 400, and sure enough, if you put that into your calculator, you end up with £1224.16 as required. Hopefully that makes sense as to where that's coming from. Assuming the man continues to invest in this way, form and sum a series to prove that he will have this in his account at the end of n years. So do you see my one that I did last time for 3 years? I hope that makes sense. So if this is 3 years, that would be an n minus 1 if their n then was 3, and then minus 2, and so on. So for year n, if we could come up with the wee formula, that would be great. So year n is going to be 400 times 1.02 to the n minus 1 plus 400 times 1.22 to the n minus 2 plus, then your kind of penultimate year is, sorry, can I can see that? It's not helpful. 400 times 1.02 plus 400. Hopefully you can see that this is now GP, if a little bit backwards. So our first term is 400. Then our ratio is 1.02 and we're multiplying by 1.02 each time then to get this. So this is a GP. Our A is 400 and our R is 1.02. So our sum then the n terms is of course going to be A 1 minus R to the n all over 1 minus R. So that's going to be, slide it up here, $400 upon 1 minus 1.02 to the n all over 1 minus 1.02. The 1 minus 1.02 then obviously gives us 400. 1 minus 1.02 to the power of n minus 0.02. So that's minus 20,000. So effectively you're multiplying that really then by the 50. 1 minus 1.02 to the power of n, and then I guess incorporating your minus in there, it's going to be 20,000 1.02 to the n minus 1. It says, hence find the least number of years until his investment exceeds £7,000. So hence obviously means using what you've just worked out. So it's our 20,000 upon 1.02 to the power of n minus 1. What value of n makes that bigger than 7,000? So let's tidy this up. 1.02 to the n, take away 1, has to be greater than 0.35. That means 1.02 to the power of n has to be greater than 1.35. Taking the logs of both sides, ln 1.02 to the n is greater than ln 1.35, n ln 1.02 is greater than ln 1.35, and is greater than ln 1.35 all over ln 1.02, and then is 15.2. So after 15 years it won't quite be there because it takes 15.2. So our final line then, hence it will take 16 years to exceed 7,000.